Hi, everyone. So next, I will go through question 4, BaseNet. So we have a BaseNet and their CPTs. So first, the question asks us to compute a joint probability. So we just find the corresponding place. So it's here. So what we have is we should use PA times PB times PC given AB. So it will be 0, 0.9 times 0.1 times 0.3, which is equal to 0.027. So next, PC equals to C given B equals to B. For this one, what we do is we can use variable elimination, and just to see if we write it out as a division form, we get PC equals to C, B equals to B, divided by PB equals to B. And then for the bottom one, we just sum out the values for A and C. So we have for the above, for the numerator, we have we need to find all the variables for B equals to B and C equals to C. So here, and no other places. So what we have is 0.8 times 0.1 times 0.1 plus 0.3 times 0.1 times 0.9, and divided by, we should sum over all the values for A and C and just leave it with B equals to B. So first we find all the assignment that has B equal to B. So this one, this one, this one. Oh, sorry, we just know B equals to B, which is 0.1. So we just put it here. And so what we get is 0.08 plus 0.27, which is equal to 0.35. Next, we just calculate C equals to C given B equals to not B. So we also find values in the CPT that has C equal to C and B equals to not B. So this one, and we sum over all the values for A, we get and this one, since it's 0, we just don't consider it, and we just have 0.3 times 0.9 times 0.1 divided by 0.9, and we got 0.03. So for the last one, for the last probability, we can use Bayes rule here. So we can write it as probability of C given B equal to B times probability of B equal to B divided by probability of C equal to C. So for the numerator, we have this one. This one will just be here. And we get 0.35 times this one is 0.1 and divided by C equal to C. And to get C equal to C, we cannot just find it directly from CPT. So we can just sum out all the values for A and B. And first, we need to find all the assignments for C equal to C, which are this one, this one, this one. And for this term, it's 0, so we just don't look at it. So we look at the previous 3 terms and just summing over their values. 0.8 times 0.1 times 0.1 plus 0.3 times 0.9 times 0.1 plus 0.3 times 0.1 times 0.9. Then we just see that we can write 0.1 and we're left with 35 over which is equal to 35 over 62. And so this will be our final answer for this question. Okay, so next, let's look at our BayesNet question B. And we're given like probability of A prime equals to that of B prime and A and this equality. And it want us to prove to calculate the value for B equal to B given C equal to C and B prime equal to B. So we want to first just write it out using the division form directly. So what we get is, so why we can do that is if we look at the question, we are given C equal to B and just the C equal to B, these 2 values. So it seems we already know this. We want to try if we can just represent this using the BayesNet as a BayesNet. So we will just see. So here we have, this will be equal to probability of B equal to B given C equal to B. Given we sum over the value for B, which will be plus probability of B equal to not B and C B prime equal to B. So we can see if we can represent it. For the numerator, for the joint probability in the numerator, we have, so if we write it out using the Bayes-Net representation, then we have probability of just this three nodes, B prime times probability of B given B prime. I think I should write it out explicitly. So times probability of B equal to B given B prime equal to B, probability of C given B equal to B. So this value we already know it's X, and probability of B, this one just equal to this one we don't know, and this one we also don't know. So why not just write out the denominator? This is just the same as the numerator plus probability of and times probability of C equal to C given B equal to not B. So we know this is Y, and we know, sorry, this should be B prime, B prime, B prime, this is B. And this, they all have B prime here, so we get rid of it. And we know this is X, and this is also X. So now just clean up the expression. We have B equal to B given B prime equal to B times X times X plus times Y. So we just want to see if we can solve these three probabilities, especially the first one. And so we can, let's look at the structure of this Bayes-Net. So this structure and this structure for A, C, A prime, B prime, and B, and that structure is very similar to the structure of A, B, C, especially the probability for A is equal to the probability distribution for A prime. So what we can do is we can also infer from that P C given B is equal to PB given B prime. This is, note that this is by symmetry. We see that their structures are the same, and so we can just infer this equation from this Bayes-Net structure. So we have, after that, we have for this probability, conditional probability, we have, this will be like this one, which this will be X, and this one will be also X. And for this, it's just a B equal to not B. So it's 1 minus X. So what we have now is X squared plus 1 minus x times y. So this will be the answer for this question. Okay, everyone. So next, we're going to look at question C. And it just led us to see which of the following conditional independence relations are guaranteed by the Bayes-Net graph. So we'll use the d-separation method to do it. So first, A prime and C. So we draw them. A prime and C. So the triple between them will be A prime, B, and C. And we see that B is not given here. If B is given, then A prime and C are guaranteed to be independent. But since B is not given, this is not correct. And next, A prime is independent with B prime given C. A prime, B prime given C. So their structure is just like this one. And so this one. And so we can simplify this to be this triple. And we learn from this separation for this triple, if the child is given, then two parents are not guaranteed to be independent. But if the child is not given, then these two parents are guaranteed to be independent. And since C, which is their child, is given, then A prime and B prime are not guaranteed to be independent. So this is also wrong. For the third one, A prime and A. So we have here A prime, A, and we can see that the triples here will be A prime, B, C, this one, and B, C, A, these two triples. And for A prime, B, C, since B is not given, then we just don't like it, they just not guaranteed. We'll look at next triple, A, C, B. And here, since since C is not given, like just like this case, if the child is not given, then the two parents are independent. So this will be an inactive triple. And on this path, we only need one inactive triple to make this path inactive. So this path will be inactive. And since this is the only path, then A prime and A are independent. So we should choose this one. Then we'll look at the last one. So B prime independent with A given B. So B prime A and given B. So we can see on this path, this is an inactive triple since we're given B. And so what we have said before is one inactive triple will make this whole path inactive. And we don't need to look at the other triple, but we can just look at as an exercise. So here, since C is not given, then A and B are also like these three are also an inactive triple. And so A and B are also guaranteed to be independent. So we also need to choose D. So the answer will be C and D. For the next question, which of the following Bayes-Net violate at least one independent relationships implied by the original Bayes-Net? So, okay, for question A prime, B, and C For the original basenet, what we mean is here. So here, the original basenet, like since this is a question belong to C, and C consider the basenet, this basenet, then the original basenet will refer to this one. So, okay, let's look at the first one, A prime, C, and B, which says if C is not given, then A prime and B are conditionally independent, are independent with each other. So here, C, if C is not given, then A prime and B are conditionally independent. So sorry, the B should be here. So here in this basenet, it says A prime and B, they cannot be independent given in any circumstances. But here they say that if C is not given, the A prime and B are independent. That's why it breaks its original independent relationship. So we choose A. For B, A, C, and B, it says if C is not given, then A and B prime are conditionally independent. So we erase them, A, B prime, and C, A, B prime, and C. So on this graph, it also says if C is not given, then like in this this triple will be inactive. So A and B prime will be independent with each other. So it doesn't violate any relation. So it's correct. So we don't choose B, and it's correct. And for C, B prime, B, and C, they're this triple. So if we are given B, then this is an inactive triple. And if we are not given B, then this is an active triple. We'll look at the previous graph. B prime, B, and C. So yeah, they are just basically the same thing, just writing in different directions. So it didn't break any independence, so we shouldn't choose C. For D, it just draw the same thing as the original one with an additional edge from B prime to C. And in a previous graph, we know if we're given B, then B prime and C will be independent with each other. However, if there is an edge that connects B prime to C, then they cannot be independent given what, like they will not be independent, like if whether we were given C or not. So it also breaks the independence relation. So we should choose D. And so for this question, we choose A and D.